Hello and welcome. Today I am introducing myself to the Coco floating point accumulators. I'm doing this because I would like to start calling some of the undocumented ROM routines, and it seems like the floating point accumulators are frequently used as inputs or outputs, even where you would least expect them. So I'm going to be writing some assembly code, some basic code. I'll be interfacing the two together. And we're going to take a look at just what the floating point accumulators look like, how they work, what they do, and all of that good stuff. So fasten your seatbelts. This is going to be a significant experience. You get the point. So I started off with the R&D function, figuring, wouldn't it be useful if my assembly language code could generate random numbers? And then I quickly saw, I need to understand FPOW first. And so I went up and looked at FPOW. And I found that FPOW is an area of memory reserved by the Coco ROM for a floating point. So it's sort of a software floating point accumulator, because the 6809 does not have floating point registers directly. The 6809 does have an opcode for decimal adjust after addition. But that's not what's going on. This is not nearly as powerful as what the Coco ROMs have. So the accumulator is primarily three parts. It's the exponent, the mantissa, which is what they were calling FPAO, and the sign. And all total it was 6 bytes. Then there are these other things that are sometimes used as part of that zeroth accumulator, but they're not necessary for the other accumulator. So I really needed to start to understand how this stuff is used. And I found that there are some routines that will convert to and from floating point numbers. There's a whole section in the Unravelled book about floating point numbers, how they're represented, with some examples, and it also lists out some of the routines that are used. So I quickly went directly to those routines, GIVABF, for example, to see exactly what they are. GIVABF assumes that you have some integer in your D accumulator, your D register, and then it does some mumbo jumbo, and by the time it's done, the floating point A0 locations in memory will then be initialized to be the floating point equivalent of whatever integer was in D. So I figured, I could just go ahead and write an assembly language routine that would call this for a bunch of different numbers, and then I could kind of get a handle on what the representation looks like and what it's doing. But I also started to wonder if maybe I was going down a rabbit hole that was going to take a really long time. Like, do I really need to understand the floating point accumulator to do anything with the basic ROM? I knew that the random number generator could sometimes generate random floating point numbers, so I figured, maybe this is just one of those few things in BASIC that uses the floating point accumulators. So I started looking at some other routines and was a little bit surprised. For example, the peak function, which you wouldn't expect would have absolutely anything to do with floating point numbers. What's the first thing it does? It assumes that its parameter is sitting in the floating point accumulator and converts it into an integer before it does anything with it. Why would peak think that a floating point number might be the parameter? And why would $CHR also expect that its parameter would initially be sitting in the floating point accumulators? Who ever heard of an ASCII code that's a decimal number? The NOT operator uses FPOW? The logical AND operator? What is going on here? Eventually I realized that the parser for BASIC, pretty much all the time it expects a number, maybe even a string, uses FPOW to parse whatever was on that line into memory. And then each of the routines that expect an integer will then have to convert whatever got into FPOW into an integer into the D accumulator. So this wasn't an unusual thing with R&D. This is actually something rather fundamental to BASIC. So yes, understanding this probably would be a good idea for me. So I decided to write a little assembly code to call GIVABF. GIVABF assumes that the D accumulator, the D register, has some integer in it, and it will go ahead and convert it into a floating point accumulator format and then store it in those memory locations. And then I could go ahead and print out what it did. So my first step was to write some assembly code that would just call it. So GIVABF lives here in memory, and this is where the floating point accumulators start. Technically, this is the exponent. This is not what they call FPA0. FPA0 is 1 byte afterward. But whatever, this is where it starts, and there are 6 bytes to it. So we're going to skip over a little bit of this, but basically what I do is I call GIVABF, and then I just copy from where BASIC likes to keep the accumulator to safe memory that I'm creating myself, so I'm sure it won't get stomped on by BASIC, but so that I can do stuff with it later. So this is just a small unwound loop that copies from the BASIC accumulator to my memory. And here's my memory right here. So that's it. That's all the assembly language code is doing. The rest of this is here to interface with BASIC. So to interface with BASIC, I'm allowed to be passed a parameter from BASIC, and all I have to do is call this documented routine, getArg, and then my parameter will be happily in the D register, which is exactly what GIVABF wants anyway. So this sets me up to call GIVABF, and then I can call GIVABF. So let's take a look at that BASIC code. There's actually a lot here because I want to print out not just the values of those memory locations, but I also want to do a little conversion so you can see it in hex and you can see it in binary. But really the only code to be focused on at first is this loop. And then, by the way, then we're done. So this loop takes what my input parameter will be and just loops it through -100 to 100. So we have like a nice selection of negative, 0, and positive numbers. And then we call the assembly language routine, which I'm calling fpconvert. And then I print it. So I just have a little subroutine to print it. And this is what handles printing all of the bytes of the floating point accumulator in the different bases. The rest of this is really just bleh. But some of it is worth understanding because interfacing between BASIC and assembly requires a few things to set up. So in the beginning, I use the clear statement to ensure that everything from 3F100 and bigger stays protected, and BASIC will promise not to touch it. And 3F100 is exactly where I have my assembly language code starting. The other thing I have to do to set up is this def user 0, which says that my assembly language routine, user 0, starts here at 3F100. I also use a variable to point to my safekeeping location for my copy of the floating point accumulator. So my copy of the floating point accumulator is right here, fpcopy. And when I run lw-asm to assemble it, it tells me where this lives. And that is right here. So this lets me know where to peek to get the answer. The other stuff is boring. This sets up for the conversion to whatever. This like initializes the screen. I'm just going to run through it quickly so that you're not too curious. But to convert to binary, I kind of slum it. I don't really do any math. I just have a bunch of strings and I stick them into an array, and then I look up into that array by a decimal version of the hexadecimal digit, and then it gives me the binary representation. And I set up the screen by just printing out the labels of where everything is going to be printed. And then when it comes time to print stuff, I just print them in the proper location on the screen depending on which byte they are. The bytes, remember, start at A0, which, as you recall, I initialized to where in my memory I'm keeping a copy of the floating point accumulator. And I just loop through all those 6 bytes. I print them in the spot that they belong, And that's it. So let's run it. Let's see what it does. So we're starting off in the negative numbers, and the first thing to notice is the sign stays FF. So as long as we're negative, it's going to be FF. The exponent is kind of staying steady here at hex 87, but that's going to change. If you look at the mantissa, it seems to be going down by 2s. And then the exponent kind of changes there, and now we're going down by 4s. Let's speed this up until we get to about 0. Alright, keep your eye on the exponent. Coming up there, oh, everybody hit 0. And now that we're in the positives, now things are looking a little bit more like they were before. Now our mantissa looks to be going up by hex 10s. Now looks to be going up by hex 8s. This has not really been very illuminating, but check out the bits. If you look at, say, the first 5 or 6 bits, it actually looks like a very simple binary counter. If you kind of just ignore the fact that there are these other bits here and that these are in the most significant bits sections, it actually looks like it's just counting and it's just going up. So it's really the combination of the exponent and the mantissa that's giving us the ultimate answer here. So let's take a look at exactly what's happening. The mantissa are the bits, the digits of the number, and the exponent tells you how much to shift it. So a positive exponent will shift it to the left, which is like shifting the decimal point, or maybe I should say binary point, to the right. A negative exponent does the opposite, so that can give you fractions. But that's kind of a lie. The exponent is represented offset by hex 80. So hex 80 actually means 0. 81 means 1. 82 means 2. That way you can represent negative numbers as an unsigned byte. So a negative exponent, say -1, would be represented as 7F. -2 would be represented as 7E, and so on. So that's just a slight adjustment, but basically what I said was true. To be more complete, I should say that the mantissa is interpreted as if all of those bits are after the binary point before the exponent is applied. So if the exponent were hex 80, which means 0, which means 2 to the 0 being 1, then all of the bits are directly after that point, so it's a fraction. If the exponent is hex 81, meaning we interpret it as 1, meaning you have 2 to the 1, meaning it's 2, then the very first bit of the mantissa would be the integer part, and the rest of the bits of the mantissa would be the fractional part. So let's look at some examples again. Maybe we're in a better position to understand. For power of 2, let's start with powers of 2. So let's say 16. The mantissa, just 1 bit. Just one. Everything else is 0. So you can think of it as just a power of 2. And what power of 2 is it? It's 5, but remember this 1 is interpreted as being after the point. So you want to shift 1 5 to the left, and the first shift just gives you 1. And then the rest of them keep giving you more powers of 2. So this would give you 16. So can you guess what 32 would be? Very good. It's the same, except the exponent went up by 1. Can you guess what 64 will be? You're a natural. Nice job. Now let's do something a little bit more complicated, maybe not a power of 2. How about just the number 3? Take a guess. What do you think it'll be? So we need 2 bits to get our 3, so our mantissa has both of these bits set, and we just need to shift them 1, 2 to the right. I'm sorry, the point to the right, the bits to the left. And so we have an exponent of 82. Have you noticed, by the way, that the sign byte seems to wildly change? Before it seemed to be just FF and 00, but now that we're doing these numbers, it's a little bit random. I don't know. I don't understand, but as best as I can tell, the sign byte is negative if the number is negative. Otherwise, the number is positive. I don't know if there's any other guarantees you can make about the sign byte other than that. Well, we're not quite done. There's still more to cover, so there will be another video coming up that talks more about floating points.